Hi, here is almost good evening, but
Okay, yeah, good evening.
yes, but thanks for putting your time. What time is it at your place?
7:30.
Okay, very early in the morning.
Just finishing my morning coffee.
Okay, okay, nice. So I think we expect more people to come.
You don't?
We do. We do.
Oh, good. Yeah.
At least a few persons I know they want to join. They are not still here, so let's wait a bit. But then in the meantime, I was thinking if you want, we could already share PowerPoint. Are you able to share it yourself or?
Well, I'm clicking on that. I don't know what's happening. I click on share, right, and then on screen.
Yeah.
And that's what I did.
Yeah, but we don't see it.
Okay. Also, do you see my video or?
At least I don't see your video also.
Okay.
I don't know about the others. Do you see me?
I do see you, yeah.
Okay.
Although you're kind of frozen. I hope I don't have problem here.
Yeah. Maybe it's only mine, but do others see Jirka or not?
No, I don't see Jirka.
Okay.
I see you and I see Antonio.
Me too.
But that's it.
Yeah.
So do we need to restart or what?
Yeah, I think now we are encountering the problem of sharing the PowerPoint. So I'm not sure if Jirka can share it. If not, maybe you could send it by email to me, then I can share it here.
Yeah, that's also an option. Yeah.
Jirka, do you hear us?
Uh-oh.
It seems we have problems, but we will see.
I think he left.
Yeah.
Maybe reconnecting.
Yeah. And so. Now I need to write him again. Hi. Not on.
Yeah.
Mm-hmm.
What now?
I think was it nice? Oh, now I think it is getting to work. So I see your video and also PowerPoint and hopefully others also.
Yes.
Okay.
Still people joining, eh?
Yeah, several people are joining. I think we are now with 24, which I expected, but maybe we wait for a few minutes before we start, maybe 1 or 2 minutes more, and then we start.
Sounds good to me.
Mm-hmm. I see myself in your shared file.
Yeah.
Do you? Okay, I think it needs to go to the PowerPoint.
Yeah.
Yeah.
That is better.
That's better. I think
So-
just before starting, just to remind everybody that we want to record the meeting. So hopefully everyone agreed. Otherwise, please let us know, because we thought that we could look at it later, and also for the people who are not present. So just that you know, we are recording it.
Correct.
And Kun, if you want, you can start.
I can start? Oh, yeah. Now,
running
Jirka,
the start.
first of all, we are extremely happy that you have time to present HYDRUS and all the features around it to the public who is now attending the meeting here. As you know, I think 1.5 years ago, we started drafting up a proposal for the European Commission, which is focusing on contaminant transport across the soil, water, atmosphere continuum. There was a call open, and luckily we won the bid, you know, and so during that proposal preparation phase, I also tried to get you on board in the project as a full partner, but you were hesitating because of all the admin related to be a full partner in an EU-funded project, and you're living in the United States, you know. So we found another way that you still can contribute to the project. We have budget reserved for you to provide some services to the consortium. And the scope of the project is on better understanding flow and transport processes of different type of contaminants. Basically across ecosystems. We have a couple of, I think, 7 use cases where we will deploy a monitoring program, also to better understand certain specific processes of those contaminants and how that really works in real life conditions. But one of the core elements of the project is, of course, that we want to improve existing models to better account for those maybe processes which are not fully addressed in these models yet. And so the data collected will be primarily used for validation purposes. And I see connections between what is promised in the proposal and what you and colleagues are doing with non-stop continuing further developing the HYDRUS model code and trying to address all kinds of different emerging contaminants. And I hope we can cooperate during the next couple of years and provide data for further validation of specific HYDRUS modules, I would say so. And we ask you to present something, which can be related to that EU-funded projects where we focus on emerging contaminants like PFAS and microplastics, but also heavy metals and pesticides. So we are extremely happy that you can present. I understand that Giuseppe is attending the meeting also, working also very much on improving the HYDRUS model code non-stop. So I expect that people in the audience might have questions, maybe either during the presentation or maybe after the presentation, and it is of course an informal meeting. So it's up to you now. So I want to give the floor to you and simply start presenting. And if one of the people in the audience have questions, please raise your hands, and I think Marus will cross-check for that and facilitate discussions.
Yeah.
Okay, Jirka, thanks. Up to you. We don't hear you.
Okay. Do you?
Yeah.
Yeah.
Better.
Okay. Well, first of all, thank you for inviting me to give this presentation describing the HYDRUS features and potential for collaboration on further developing this software. I know that this workshop is planned for 90 minutes. I didn't know what's related to how much in depth to go about the code, and so I will have some kind of a general introduction into HYDRUS, our team, our history. Then I will describe all the different capabilities which HYDRUS has, So I will describe all the older, I call them older because they were developed over the last 20, 30 years, specialized HYDRUS add-on modules, which gives HYDRUS some special capabilities. Then I want to describe some of the recent models that we developed, so that really relates only to the last 3 or 4 years. And finally, since I know that you are interested mainly in the microplastic, PFAS, and that stuff, so I want to briefly discuss what are the capabilities of the HYDRUS in that area. So, but first, let me introduce our team. So I'm working on development of this code or as this software with multiple people. You see them listed here. So first of all, it's Rien van Geruchtem, with whom I'm working for some 35 years already on these modules. Then Mirek Šejna, who is involved mainly in the development of the graphical user interfaces rather than the computational modules. Then Didier Jacques, with whom we are working mainly on the development of HP programs, which can do quite complex biogeochemical simulation. And finally, our recent addition is Giuseppe Brunetti, who is doing a lot of development in recent years. So first, let me introduce myself. So I am from Europe. I'm from Czechoslovakia, where I got my degrees, but currently I'm working at the University of California in Riverside. And I'm in Riverside for the last 35 years, but for about 20 years at university. And my specialty is numerical modeling, development, numerical models, and their applications. I don't know if I need to introduce Rien van Geruchtem, maybe only to the younger audience. So he was my boss initially when I started as a postdoc in Riverside. He was a research leader at the US Science Laboratory, and I consider him a godfather of our discipline of Wade zone modeling and soil physics, because he developed most of these concepts which we are often using. He's one of the most widely cited, if not the most widely cited, researcher in the field of soil physics and hydrology, and he has over 100,000 citations. And as you can see here on this slide in the middle, he got all these various different medals. So he's a fellow of 4 societies. And last year he receives the Wolf Prize, which is considered the Nobel Prize for Agriculture, so the highest award you can actually get in our field. And he's from Holland, so he's from your neighborhood. Miroslav Šejna, he's a mathematician, so he's probably not well known in our community. He works on numerical modeling as well, but a completely different stuff. He works on transonic and flow around objects and in turbine cascades and stuff like that. That's where he got PhD. But with him, we are working mainly on the developing of the graphical user interfaces for HYDRUS and other codes. But as you can see in this slide here, above his photo, he can do quite interesting simulations around different objects and development of flow fields and stuff. I already mentioned Didier, so he's from Belgium Nuclear Research Center. And with him, we coupled HYDRUS with FreakC, and FreakC is a biogeochemical model which provides tremendous capabilities to our code. And finally, Giuseppe. So I started working with Giuseppe, I think, about 6 years ago. And when he was a PhD student, and since then he developed quite a few specialized HYDRUS modules, and I will mention some of them: ferro, dynamic plan uptake, cosmic ray neutron model, etc. I still have him listed as working in Vienna, Austria. I should have updated his slides, so he's now in Italy. Okay, so HYDRUS models. So it's a software package or multiple software packages which can simulate flow and transport in 1, 2, and 3D. They are used by thousands of users. We have some 80,000 people registered actually on the HYDRUS website, which is incredible. And if you look in the literature, research literature, you can find over 5,000 peer-reviewed journal articles which used HYDRUS to simulate various types of processes. Historically, HYDRUS was consists of two software packages. One was HYDRUS 1D, which was a code simulating flow in one dimension. And this code was and still is in the public domain. But we stopped developing this code about 4 or 5 years ago. And it remains as it is. And we will not be doing many modifications of this code. And then the second piece of software was the HYDRUS 2D, 3D, which simulated flow and transport in 2- and 3-dimensional geometries of practically any shape. The flow and transport processes in 1D and 2D, 3D are quite similar, in most cases identical, except for the dimension. But then HYDRUS 2D, 3D has a few more specialized modules than HYDRUS 1D. And both models are numerical models, so which means that we need to define the transport domain, and then we divide it into small pieces or small elements, so-called finite differences, finite element, finite volumes. And I give here some examples for 1D on the left, for 2D in the middle, and then for the 3D on the right. And we simulate flow and transport in the subsurface. Our focusing is on the radon zone. We can consider saturated zone as well, but that's certainly not our focus. Our focus is radon zone, that's the zone between soil surface and groundwater. And we can simulate processes at many different scales. So in this slide, I tried to show that we can go from the small scale when you do laboratory experiments on the column scale. You can apply the code at the field scale and at larger scale up to catchment, although I'm not in big favor of such application. Similarly, in the temporal scales, you can go from short-term experiments on the scale of hours, but you can also simulate hundreds of years if you want to see some long-term effects of, let's say, climate change. There's many types of applications, so I typically divide them in 3 large groups. So agricultural applications, where we evaluate processes in the root zone, and you see on the left all the different types of hydrological processes. We can also deal with many different chemicals, from fertilizers, pesticides, fumigants, pathogens, nanoparticles, etc. Then there's a lot of industrial applications, evaluation of different municipal and industrial pollution, landfill covers, various leaks, etc. And then there is also a lot of environmental or ecological applications. HYDRUS has a module for carbon dioxide transport and production, for example. That's the oldest module which we have. And so it can simulate soil respiration, nutrient transport, and so on. Okay, well, this slide shows the history of the 2D code. And as you can see, we track the history all the way to the work of Shlomo Neumann, who was one of the first who actually worked on numerical modeling in early 70s. And he developed the program ANSAT when he was still in Israel before he moved to University of Arizona. Then at the same time, in 80s and 70s, actually, Rien van Genuchten was working on numerical models at Princeton, where he was postdoc, and at Mexico Tech, I believe, in Socorro or Las Cruces. And so he developed various new numerical techniques, various schemes, etc. And when I came to the United States in 1990, so I started with what we developed back when I was still in Prague as a master student, and combine that with all these latest developments and put that into the program, which was called SWMS2D, which we released into the public domain in '92 at the US Salinity Laboratory. And this period until '95, I called like DOS era or pre-Windows era. And then in '94, we started developing with Mirek the graphical user interfaces and package that into the software packages. So it was not just the computational module. And then we started using the name HYDRUS. Initially, we started with HYDRUS 2D. Then we added HYDRUS 3D in 2006. And then we added additional modules. And well, you can see all the development. And today we are on version 5, which we released in 2002, and I will give a little more information about that. History of HYDRUS 1D kind of mirrors that, except the very beginning, because in 80s and 90s, pretty much everybody was developing their own codes. So we were in Prague with Tom Fogel and Miroslav Scheer developing these models, and without much input actually from Reen. But then again, when I came to US, to Riverside, I combined this effort and we started releasing these codes under the name HYDRUS. And this HYDRUS 1D, which as I mentioned was public domain code, so we merged that in 2002 into one single package, which can do everything from 1D, 2D to 3D. And we call it version 5 to kind of avoid confusion, because HYDRUS 1D already had version 4 and HYDRUS 2D, 3D was version 3. So we skipped 4 here and went straight to 5. So this slide shows this recent development in 22, where we merged HYDRUS 2D, 3D version 3 with HYDRUS 1D version 4. And now we need to develop only one single package, so we don't have to be developing multiple packages. To incite people to get this new version, so we included many new modules which we developed in recent years, mostly during the COVID time, when we had much more time to play with the computer. And so we added these modules such as particle tracking, COSMIC modules, CRI, PFAS. That's also a relatively new module, Fumigan, etc. So the standard code can simulate water flow, solute transport, heat transport, and other processes, carbon dioxide transport. And it is relatively general in doing that. So it solves Richard's equation, and it allows you to use various models of solid hydraulic properties, various analytical models. And I will have another slide for that. It can consider hysteresis. It can consider multiple ways how to deal with the root water uptake, both empirical and physics-based model. It can compensate uptake. So uptake can be compensated, uncompensated. And it can also reduce the uptake due to different stresses, osmotics, pressure, and so on. The code has options to simulate preferential flow, as well as isothermal and thermal, liquid, and vapor flow. In terms of solute transport, we try to be very general. And so we consider convective, dispersive transport in the liquid phase, diffusion in the gas phase, and then various interactions between different phases. Between solid and liquid phase, we can consider linear and nonlinear interactions. We can also consider now in the PFAS module linear and nonlinear interactions between the liquid phase and air-water interface. And we consider also linear equilibrium between liquid and gas phase. That would be Henry's law. And then various productions, first, or various reactions, first and zero water. And the code can also consider both physical and chemical non-equilibrium. So that means different types of non-equilibrium caused by physical or chemical reasons. Again, we have a root nutrient uptake term, which can account for both passive and active uptake of nutrients. Heat transport, we initially added mainly so that we can account for the temperature dependence of various reactions. But later on, we implemented fully coupled heat transport, vapor flow, heat transport due to temperature gradient, due to pressure gradients, etc. And finally, we have multiple algorithms to do inverse optimization. Historically, we used to have only Marquardt Levenberg, but Giuseppe added some global search algorithm in the recent version of HYDRUS. Okay, so we are solving Richards equations in the basic code or basic module, but also in all the specialized modules. And we allow these different models to describe soil hydraulic properties. So we allow Brooks and Corey, Van Genuchten, Vogel and Cieslerova, which is really modified Van Genuchten, then dual permeability model of Durner, Wolfgang Durner, and then Kosugi. And recently we have added the new functions, which we call Brunswick type model, which was developed by Tobias Weber and Statis Diamantopoulos, who helped me to implement that in HYDRUS, which adds to the capillary soil hydraulic properties also options to consider non-capillary processes. We work on a lot of applications now, which include managed aquifer recharge, either from surface basins or from wells. And these systems often suffer from clogging. And so in the recent version, we also added some options to account for the changes in hydraulic properties in time. Root water uptake. So historically, we solved this problem using the empirical models of FADES and Van Genuchten, with the possible modification developed by Nick Jarvis for compensation. In the recent version, in the last version, which we released only this year, we added also some process-based model to describe the root water uptake. And so we implemented 3 different models, NEMA and HEX, which is driven by the pressure gradient, de Jong-van Leer model, which is driven by the flux potential, and then finally the Couvreur model. And we describe all these models and its implication in this manuscript, which Jan van der Bork was a reviewer of, and he made us work very, very hard on this paper and on correctly implementing these models. Recently also, well, we always had coupled movement of water vapor and energy in 1D, but recently I get a lot of requests, mainly from Germany, on implementing this also in 2D, 3D, because apparently in Germany they need to solve this problem of temperature fields around buried high voltage cables transferring electricity from power station in the North Sea to Bavaria. And so we added this option, and this option is currently available. So you can see the modified Richards equation, where you have also term accounting for flow due to temperature gradient, and this is heat transport equations, which accounts for the vapor flow, temperature gradient, pressure gradients, etc., or latent heat, and so on. Okay, the solute transport. So the general code on the standard module can simulate transport of single ions, as well as particles such as colloid, viruses, bacteria. But it can also simulate transport of multiple ions, but this is restricted only to the sequential first-order decay chains. And there's a couple of examples you can see on this slide: radionuclides, nitrogen species, so that's something you might be interested in, pesticides, chlorinated hydrocarbons, pharmaceuticals, etc. And then if you want to consider something more complex, than this, you need to use some of our specialized modules, such as the ANSATCAM module, which simulate fate and transport of major ions, the HP 1, 2, 3 modules, which can consider various very general biogeochemical reactions. We have wetland modules which simulate biological and chemical processes in wetlands. And then we have also module for colloid facilitated solute transport. And now we have also the PFAS module and others. Historically, HYDRUS had only one optimization algorithm, and that was the algorithm which everybody was using from 50s pretty much. That was developed by Mark von Leeuwenberg, and it was a local search algorithm, so it was a gradient type algorithm. We were always criticized that we don't have a global optimization routines because people want to do the foolish stuff of optimizing 15, 20, 30 parameters, which cannot be done with Mark von Leeuwenberg. And so Giuseppe implemented it into the recent version, but only F1D currently. Various global optimization routines. So we implemented the classical particle swarm optimization, but he also developed 2 additional algorithms recently, and those are also available in the code. And this is the window where you can select these optimization algorithms. Well, HYDRUS has obviously a relatively sophisticated graphical user interface, which make it very easy to work with the code, specify parameters, define geometries, etc. And I have here 1 or 2 examples. Okay, now let me talk about these modules. So what is common for all these modules that they simulate water flow, but then additionally they can do something else. So the HP models developed with Diederik Jacques. So here we coupled HYDRUS with FreakC to be able to address various biogeochemical processes, which you cannot do with the standard code. In the standard code, you can simulate degradation, you can simulate sorption, but you cannot do, for example, cation exchange, you cannot do precipitation dissolution of minerals, you cannot do competitive sorption, etc. Then we have a module ANSATCAM, which deals with the issues of cell, which is obviously a global problem in many countries. And so this module simulates transport of major ions and interaction between them. And here you can do cation exchange, you can do precipitation dissolution of minerals such as calcite, dolomite, etc. Then with Günther Langegraber from BOKU in Vienna, we developed the wetland module, which considers various biogeochemical processes in constructed wetlands. Then we have SEARIDE module, which can simulate particle transport. And under the term particle, I include everything which has the size. So from virus, very small viruses, the nanoparticles, colloids, up to the sizes of bacteria. And obviously the microplastics would fall in this category. We have a module which we call dual perm, which can simulate dual permeability flow. So that's the model which attempts to deal with the preferential flow, which is one of the most frustrating processes, as you probably know. Then we have a module for fumigant. That's a really specific application in California, where fumigants are widely used. And then we have also a package for ModFlow, where we try to give capability to ModFlow to simulate flow in the Vado zone. So let me give you slightly more information about these old modules. So FreakC, so here we take HYDRUS, which simulate flow, transport, heat transport, root water uptake. We added also an option to simulate gas transport because a lot of these biogeochemical system depends on concentration of oxygen, carbon dioxide, etc., and those are transported in the gas phase. And then we coupled that with the FreakC, which is a biogeochemical model developed by David Parkhurst and Tony Appello at the USGS. It is a very general model, very widely used. It can consider all these available chemical reactions which you see here: aqueous complexation, redox, ion exchange, surface complexation, precipitation, dissolution of minerals. And very nice feature of this code is that you can use thermodynamic databases to define these reactions, but you can also develop your own species or define your own species, define your own reactions. You can remove certain reactions from the system and instead define them using short basic codes and describe their kinetics, etc. So it's a very powerful, really, solver which can solve these issues. It is not easy to use, so we don't have too many users. If you look into the literature, there will be probably like 100 applications only of the HP models compared to, you know, thousands of applications of HYDRUS. This slide tries to explain slightly how this model works. So imagine that you have a contaminated column with zinc, some heavy metals, zinc, lead, cadmium, and you then leach this column with calcium chloride. And then, so you start FreakC. FreakC will consider all the reactions which occur in the system, so cation exchange, surface complexation, aqueous complexation, etc. And it will calculate the breakthrough curves of all these species which are involved in this, so including heavy metals and then the major ion, etc. We have many other applications. I just give here some list: transport of heavy metals, transport and mineral dissolution of minerals, biodegradation of different organic chemicals. We simulated many types of radionuclides. Obviously, that's Diedrich's focus, so radionuclides and others. I use that in one of my grants to simulate transport of explosives such as TNT, RDX. And we can also consider in this code, let's say, property changes, such as how porosity will change as a result of dissolution, precipitation of minerals. And so it's a very, so it's a very general model. Okay, Ansatkan, that's actually the oldest module which we developed. I was hired to develop this in 1990 as a PhD student. And this module focuses on modeling carbon dioxide transport and production in the soil, and then the major ion chemistry reactions and transport. The major ion chemistry requires knowledge about carbon dioxide because it affects pH, it affects dissolution of calcite, etc. And that's why we have also carbon dioxide in this module. And this module solved this fixed geochemical system. So contrary to HP1, which is a general solver where you can define any species you want to consider, Ansatkan is fixed only for this particular system, which consider only major ions. So you cannot use it for heavy metals, etc. But there is a lot of very important applications around the world which can be addressed using this module. So you can evaluate sustainability of various irrigation systems and to evaluate whether, you know, you get salinization, solidification of the soil. You can use the module to simulate reclamation of sodic and saline soil. You can evaluate release of various brine waters during mining operation, etc. So there is a lot of applications, and I can see this module used often and often in the literature. I have only one slide which shows the applications of this module where we tried to evaluate the effectiveness of HYDRUS to simulate fluxes water content, concentration of individual ions, calcium, magnesium, overall salinity expressed as EC, sodium absorption ratio, exchangeable sodium ratio, etc. And I give here some references where we publish these applications. The code exists also in 2D and 3D. Wetland module, I don't know if it's part of your project, but this is a module developed by Gunther Lange-Graber, and it can deal with the processes in constructed wetlands, also natural wetlands as well. And there exist different types of wetlands with horizontal flow, vertical flow, and those are completely different systems. Vertical flow, constructed wetlands, in these systems, you have mainly aerobic and anaerobic reactions. In the horizontal flow wetlands, you have mostly anaerobic reactions. And so we actually have two wetland modules for these two different applications. Just to show you the complexity of this module is, I have this slide, which lists here all the different species or components which you consider in this model: dissolved oxygen, different nitrogen species, different types of bacteria, heterotrophic, autotrophic, different pools of organic matter, etc. And then different reactions between these modules. And all these reactions are described by monotype equations, kinetic equations, to account for all the interactions between these components. And I will not go into more details about that. SEARIDE. That's a module which simulates particle transport and particle facilitated transport. So the focus is here on this facilitated. And what is the reason, right? So many contaminants should be relatively mobile. Let's say radionuclides, they have retardation of thousands, sometimes millions. Phosphorus should have relatively high retardation factors, but we can certainly have an evidence or find evidence that these contaminants travel long distances. So they travel much faster than we would predict based on the retardation factors. And the reason why these contaminants travel long distances is because they can attach themselves or sorb to colloids, which are much more mobile, which move at the same rate as water and sometimes faster than water, because they are constrained to larger pores. And there is evidence for this for many different compounds: heavy metal, radionuclides, viruses, pharmaceuticals, pesticides, nutrients, etc. And so we developed this module, so which can account for this. So when we deal with the transport of particles, we consider, that the particles are dissolved in the liquid phase, and then they can attach to the solid phase or detach from the solid phase. So those would be, let's say, chemical processes. At the same time, because they have certain size, they can get stuck in air-water interface. And then we have also processes of attachment, detachment to the air-water interface. Now, if we add into the system the chemical, some chemical compound, so this chemical can be dissolved in the liquid phase. So this is liquid phase. But as you can see, it can also attach to the colloids, and it can attach to the colloids which are in the liquid phase. It can attach to the colloids which are attached or strained. And the chemical can also interact directly with the solid phase, obviously, right? KD, the retardation. And it can interact kinetically or instantaneously. And so we have relatively complex systems, which you see here, where each of these arrows is ordinary differential equations, which we need to solve, and we need to solve them all simultaneously. And as I mentioned, there's a lot of application for that. So the first application I worked on was with Lipping Pond during my trip to New Zealand. where we simulated transport of heavy metals attached to the bacteria in the aquifers. And the bacteria, since they have a relatively large size, so they are constrained to fractures and larger pores, and they move much faster than the average water velocity, and then they can carry these contaminants. Okay, another module, dual perm. So if you look at the subsurface, obviously it's almost never homogeneous. You can always see some macropores caused by decaying roots, by macrofauna. You can see different types of layering because of the sedimentation process. You can see fractures in fractured rock, etc. And you cannot describe this system using standard Richards and convection dispersion equations. And so scientists developed various approaches which are typically based on the hypothesis or assumption that you have multiple pore systems and that water and chemicals move differently in these different pore systems. Most common application is that you have two pore systems, that water in one of them is immobile and water in the other pore system is mobile. And that would give us these dual porosity, the models, which are classical models used in soil physics from 70s. Then in 90s, people came with the idea that maybe water can move in both of these systems, although at a different rate and under different conditions. And that came to the concept of dual permeability models, where you have two overlapping pore systems and water can move in both of them, but at different rates. And in the literature, you can find different terms for these two systems: matrix fractures, macropores, macropores, interporosity, intraporosity, etc. But they all mean pretty much the same. So what we have in HYDRUS, we have this suite of approaches from the simple uniform flow based on Richards and CD equation. That's the standard approach. Then we can have this mobile-immobile model where we divide water into two regions, and solute can move in one region and is immobile in another region, but it can diffuse between them. So that's the classical mobile-immobile water concept. Then we generalize it slightly, that we applied also for the water, that you can have mobile and immobile domains. And finally, we can have this dual permeability model where you have fast movement in the macropores or fractures when they are active, but then there is no flow once they are inactive. And then you have slow flow in the soil matrix or rock matrix. We describe all these models in this paper in general. So these models describe physical non-equilibrium. So non-equilibrium in this system is caused by physics. You can also combine it with chemical non-equilibrium. That means that you have there some kinetic reactions with respect to sorption. And that would give us these additional modules, which we can also account for. The simplest chemical non-equilibrium model would be that all the sorption is kinetic, and then we call it one-side kinetic model. That's the simplest model, but this model was not very successful in describing the experimental data. So that's why, again, soil physicists came up with this concept of two-side model or two-side sorption. And in this model, we divide the sorption side into equilibrium and non-equilibrium or kinetic sides. And this is, again, classical approach, which was developed in the 70s and was very widely used and very successfully used to simulate transport of many different compounds. We generalized this model into the two kinetic sides model, where we have two kinetic sides, and you can have different processes on these different sides and different rates at these different sides. And this is the module which we use for the particle transport. So we can consider one of these reactions to be attachment, detachment. The other one can be the straining, or it can be the attachment, detachment to the air-water interface, etc. So this is the model which is used for transport of particles, including microplastic, but mainly viruses, bacteria, etc. And I was looking at the literature. This model was used in over 200 publications already dealing with these systems. These are purely chemical non-equilibrium models, but we can also combine them with these physical non-equilibrium models. And so we can combine it with the two-side sorption model, with the mobile-immobile model, and we can combine it with the dual permeability model. So in this dual porosity model, where we have mobile and immobile water, we consider instantaneous sorption in the immobile zone because the residence time in the immobile zone is relatively large, so there's enough time to reach the equilibrium. And then we have a two-side sorption in the mobile zone, where the flow is fast and you may not reach equilibrium. And finally, dual permeability and two-side model, most complex, with most parameters, most difficult to apply. This is where you can choose these models in HYDRUS graphical user interface. So these are physical non-equilibrium models, and these are chemical non-equilibrium models. And it exists in 1D, 2D. We do not have this in 3D. Fumigants, I will skip that. This is a special applications which I developed for California EPA. In California, we use fumigants to sterilize the soil before we plant vegetables and fruits. And these fumigants were destroying the ozone layer. So there was a lot of research in finding replacement of these fumigants. And so I developed for them a specialized module, so I will skip that. And then finally, one of these old modules is HYDRUS package for ModFlow. So this work was carried out in three stages. First, in around 2007-8, I was working with Sophia Seo and Aileen Potter from the Colorado School of Mines, and we implemented the HYDRUS module directly into the ModFlow to account for processes in the Vado zone. Then in the second stage, I worked with the PhD student Sahila Begum, and we expanded this HYDRUS package from ModFlow also to solute transport. And so we can also simulate solute transport in the Vado zone and then in the groundwater using, I think, RT3D, which is one of the packages. And currently we are developing a model which couples three different models, which couples ModFlow, couples HYDRUS, and Kineros for overland flow. And the way we are developing is only through the Python scripts. So we keep these models independent, ModFlow, HYDRUS, Kineros, and we just call these modules and let them interact. And so these modules can be kept developing, and we don't have to modify our interface between these three modules. We are slowly getting to be able to apply it at the catchment scale. Well, the idea behind the HYDRUS ModFlow is that we describe the flow in the groundwater using ModFlow and solve the Boussinesq equation, and then flow in the Vado zone we describe using Richards equation, and we solve it by HYDRUS. And the idea is that the flow in the unsaturated zone is mainly vertical, so we can describe it by 1D code, although we can have multiple verticals around the catchment to simulate all its complexity. With Jan van der Boort, who is, I saw him on the call, we work on the application with Sahila Begum, where we applied this to simulate the flow and transport of atrazine in some, I guess, aquifer in Germany. Okay, so now the recent or new modules, and I will go relatively quickly through them. So Giuseppe developed the Faro modules where we use HYDRUS 2D to simulate processing at the subsurface, and then we link them with the solution of this 1D zero inertia module to simulate flow over land. So we have one equation for the surface flow, and then we have multiple 2D cross sections by HYDRUS to simulate processes in the subsurface. This is how the module look like in the HYDRUS interface. So you describe the geometry of the Faro, you describe the roughness of that flow, and then you get information about the advanced recession of the flow. In the Faro, you get information about flow and transport in the subsurface at these different locations along the Faro. You get all the information about the masses, how much water, how much chemical infiltrates at different places, and so you can optimize the system. The cosmic module is another module. That's an interesting one. I was contacted by Harry Verhaken whether I would be interested in working on that. And I told him that yes, I would, but then I'm going to the SSSA meeting, so I can start working on it only in 2 weeks or something. I mentioned this idea to Giuseppe, and before I came back from the meeting, the module was developed and the paper was written. What is the idea here? So there are these cosmic neutron probes, and they measure cosmic neutron fluxes. So the Earth is constantly bombarded by these neutrons. They penetrate the ground. They get slowed down. Some of them get sent back to the atmosphere, and the flux of these neutrons depends on the water content. An advantage of this tool is that this probe can measure average water content at a scale of radius of, I think, like 100 meters and larger. So we get average water content on the large scale. And so we thought that we can calculate these fluxes and then we can use them for calibration. We can actually calibrate soil hydraulic properties at the large scale, not at a small sample which we measure in the laboratory, but we can get effective hydraulic properties for the large scale, which is something as a holy grail of hydrology, to get the parameters for the large scale. So we simulate flow transport with HYDRUS. We obviously have knowledge about water content, and based on the knowledge of the water contents, we can calculate these neutron fluxes. And then we can calibrate the model against the measured neutron fluxes and estimate soil hydraulic properties at this large scale. Okay, dynamic plan uptake model. That's a recent development also. So we were contacted by Radka Kudeshova that she is running a lot of experiment where she irrigate water with certain contaminations, some pharmaceuticals and hormones. And then she grows in these pots some plants such as vegetables, tomatoes, lettuce, etc. And she's interested in finding how these plants uptake these chemicals and whether we would be able to model something like that. So again, when we have a problem, we approach Giuseppe, and Giuseppe developed this dynamic plan uptake module where he added to the classical HYDRUS, which simulate processes in the subsurface. He added this plant component, and he also added the flow and transport through the plants. So the model looks like this. So it's a compartmental model where we have HYDRUS simulating processes in the subsurface. And then we have 4 pools or compartments representing plants, roots, stems, fruits, and leaves. And we follow water with the transpiration stream from root water uptake from the soil through the roots, stems into fruits and leaves, and we at the same time consider also transport of these various chemicals. So this is a very interesting applications, as you can see, which we were able to publish in some nice journal, WRR, ESNT, Journal of Hazardous Materials, etc. And here I show one application where we simulated the transport of carbamazepine and some of its metabolite in the 3 different vegetables, lettuce, spinach, and arugula. Particle tracking. This is something which I actually developed when I was a master student, where I had my first code. It was in early 90s when I had my first code based on the Richards equation solution. And I knew that particle tracking is very widely used in 2D and 3D to visualize the transport in the aquifers. But I thought, what would happen if I developed something similar for the Vado zone? And so simply doing some kind of very simple mass balance calculations, which you see on this slide, I could then get the visualization of flow and transport in the Vado zone. And so here you see 2 examples, one for the relatively arid regions where the particles, which are initially distributed in some way, don't move much or move upwards towards the root zone due to capillary rise. Then the other example here is humid for the humid regions, where you can see that these particles move downwards and can characterize the recharge. You can see that I have some particles initially distributed in the profile, but then I can also generate them at the surface with different rainfalls, etc. And if you analyze the output from these applications, what you can get is you can get travel times, right? Because each of these particles, you can calculate how long it would take to reach the groundwater. So you can get travel times for each of these particles. You can evaluate it statistically, and you can get some kind of frequency distribution of these travel times. And that's obviously important information for these different managed aquifer recharge applications. You can also use these particles and generate graphs of water age. So you would see how old the water at different depths is. And this is something ecologists are, for some reason, very interested in, whether it's a new water and old water. So there's this two-type water concept often used also in the isotope applications. Environmental isotopes. So I had a PhD student, Tiantian Zhou, who was working on this recently. We work on this topic over decades. So I started working on this with Christine Stump from Boku in Austria already in 2012, when we developed a special version of HYDRUS which could consider isotope transport without considering fractionations. So that means that all isotopes were allowed to leave with evaporation. And this is applicable in humid regions, but you cannot really use it in arid regions. In the recent version, I added this also into 1D and 2D, where you can have no or constant fractionation. So you can say that you have no fractionations, everything leaves, or you can say 95% leaves, so you can get some kind of fractionation. And Tiantian developed a version of the code which can calculate fractionation based on the environmental factors such as temperature, vapor pressure, etc., using these models, Gonfiantini and Craig and Gorton, and we are planning to implement that into the standard code. Okay, and then the finally fast, then now you may start being a little interested in that. So in the convection dispersion equation, which accounts for the solute in the liquid phase, solid phase, now we have to account also for the sorption to the air-water interface. So that's the special features of the FOSS chemicals, that they sorb also to the air-water interface. If you deal with the groundwater, you don't have to worry about it, and you can use the standard code because there is no air-water interface, and you can consider only sorption and dissolution. This makes it quite complicated, because contrary to the sorption to the solid phase, when the solid phase is a constant, has a constant size, air-water interface is very dynamic. It changes with time. You destroy air-water interface during imbibition. You generate interface during drying. And so that makes it quite complex. Fortunately, there is a simple way to calculate air-water interface from the retention curve. And in our first version of this code, we considered simply nonlinear sorption to the air-water interface using this Langmuir-Freundlich isotherm. This slide shows you the extent of the air-water interface as a function of water contents for 12 different textural classes based on the USDA triangle. And you can see that the interface can become really huge, 100,000 centimeter cube per centimeter squared per centimeter cube. And if the water content change in this range, so you can go from 100,000 to 0, right? If you saturate the soil. And you can imagine that that will lead to the release of the chemical into the system or fixation of the chemical on the system, depending on the conditions. If you do the simulations, you will also see these kind of sudden changes of concentrations, which is not typical for normal solutes. And that's because of these dynamic changes of the extent of the air-water interface. In the recent version, I also added two-side sorption concept for the air-water interface, so you can have instantaneous and kinetic sorption to the interface. We can also account for the fact that these chemicals also influence the various properties such as contact angle and viscosity, and that has impact on the pressure head and conductivity, and that influences flow and transport. And so we use these simple empirical functions to describe that in the standard module which we have now. So this is effect on the pressure head, and we use the scaling approach which we have in HYDRUS to deal with that. And this is then the effect on the kinetic viscosity and conductivity. Yeah, in the recent version of HYDRUS, we added some additional graphical capabilities, so you can have these types of results for 1D applications, so where you have time on the horizontal axis, depth on the vertical axis, and then you can make graph for these different species. In the version 5.4, which we released this year, so this is what we added there. So we added this global optimization routine, particle swarm, etc. We added relative gravity. In US, right, we are fortunate to have Elon Musk here, who will send people to Moon and Mars, and so NASA is funding research to simulate what happens with flow at different gravity fields. So we have this option now in HYDRUS. We implemented this Brunswick model for soil hydric properties this year, this alternative root water uptake models, that's also new. Clogging is new, two-side sorption. So those are all new options. So you can see that we still keep on developing this model quite a bit. The plans we have is for competitive blocking, freezing, thawing. We do have a module which can be downloaded from the website, but it's not part of the standard code. We currently work with Giuseppe again on how soil hydraulic properties can change in time as a function of tillage. We have an options for multiple vegetations, and so on. Yeah, and so these are some other plans to add modules to be able to do Bayesian analysis, different types of sensitivity analysis like Sobol, Morris, etc. Yeah. There is a tutorial book where we carry out, I don't know, some 20 different examples where people can go along and analyze these examples and learn how to use HYDRUS. This is for 1D. I was planning to do 2D, 3D, but I think simply I started doing it, but I don't have time to finish it. If you are interested in the code, you should certainly take one of our short courses. This year I had short courses in Prague, in Peru, in South America, in Africa, in Cameroon, and online in US. This year we planned something similar. So we planned on-site course in Prague, and then online courses for US and again Asia and Oceania in the fall. And I'm sure most of you know how beautiful Prague is, and you can hear from your colleagues how great these courses are. Okay, this was this part. Now I want to focus on these PFAS and the new developments, which I think we can do, right? So I want to mention three things.
Jirka, thanks so much. How much time do you think it's needed for the rest of your presentation?
Let's say 10 minutes, but this is really
so we
relevant.
still have time at the end for the questions.
Yeah.
Okay, good. Thanks so much.
This is relevant for your application.
Yeah, this is the part. Yeah, we will listen. Thanks so much.
Okay, so particle. It's I just searched, applications of HYDRUS to microplastics, and you see I found immediately, quite a few in recent years. You have seen this slide, so we consider these things. This is the governing equations. We have one side which consider attachment, and we have second side which that's how we describe. That's being used also for microplastics. We have different types of blocking functions. So not only these two, but also we can combine them. We have this random sequential adsorption, and we can also account for ripening, which means that you have more absorption the more attached particles you have. We can also calculate attachment coefficient using filtration theory. So that's the engineering theory where, we can calculate single collector efficiency using this. So what is important here is that the attachment and detachment of these particles depend on chemical conditions. And so if you have high ionic strengths, the chemicals are attached very readily. If you have low ionic strengths, the chemicals are released. And we work on this with Scott Bradford about 10 years ago, where we accounted for these different changes in ionic strengths, and then the potential release of the the compounds as a function of ionic strengths. And so this is so we would carry out column experiments. We would attach the particles. We would get the breakthrough curves through the early stage with the high ionic strengths. Then we would lower the ionic strengths. That would release the chemicals. We would lower it again, etc., etc. So we developed this. It is not in the standard code. So I have this code somewhere. So and I'm pretty sure that this would be relevant to microplastics as well. Then transient waterfall conditions, they affect that also. So they affect the torque balance. If you have imbibitions or draining, that affects that. Also, if you have particles which attach to the air-water interface, then you're destroying or creating air-water interface during imbibition and draining. And again, we developed a module for that with Scott Bradford. Again, we already published that about 10 years ago. And again, we had some applications where we would be changing saturations So increase saturation, so we would be decreasing the air water or destroying air water interface and releasing these particles. We also work on, what happens with these particles when they move at the pore scale, right? So they move into these kind of, they create some kind of eddies into these parts. And so we developed multiple hypotheses and models for that based on the dual permeability model to account for the higher attachment and detachment in these spaces of the pore scale. We developed multiple of these modules. Again, this is not in the standard code. I could find it somewhere, probably in my backups. So this was one model which we published in 2009 with Scott, and another one here, 2011. Future developments which I thought about doing is microplastic transport under transient water flow, transient chemical conditions. So those are which I just described. Attachment, detachment coefficient function of various transport and chemical parameters. If you attended Scott Bradford's presentation, I believe last week in Utrecht, so he's trying to develop some general model which would predict attachment, detachment based on various conditions in the system. So he's trying to develop a general model which we could potentially implement in the code. Then a lot of the transport experiments, which when people study the transport of particles, they typically use only one size particles. They would have colloids of certain size. If you have a mixture of these chemicals, they behave very differently, right? Because then the particles also attach to each other, smaller particles to the larger particles, etc. So if you have a mixture of particles of different sizes, and for microplastics, you will certainly have that, right? Then the system behaves very differently, and it might be necessary to develop different approaches. For example, obviously they will compete for the attachment sides, but then they can also add additional way of sorbing. So that's something one should look at probably. Okay, PFAS. What I'm doing with PFAS, I already, again, we released this code only recently, I think 2 years ago. I was looking for some applications, so it was really slow, but this year already I have seen some 6-7 applications, so it's slowly exploding. Okay, so what we are doing it, I already described this. So we consider solid phase sorption, instantaneous, kinetic. Then we consider air-water interface sorption, again, kinetic and instantaneous. And what I'm implementing, and we can account for these effects on the hydraulic properties. But what I'm doing now is I'm looking at the multi-component transport of these chemicals, because they are always a mixture of these chemicals, right? If you have contaminated sites. And what happens is they do affect the hydraulic properties, so tension, conductivity, and you can describe that by these Shishkovsky equations. These equations, so I'm implementing these equations right now in the code, but they also compete for the sorption sites, right? So if you have multiple of these chemicals, so you should consider something like Langmuir-Shishkovsky isotherm equations where they compete for the sorption, right? Because here you have a sum of different chemicals sorbed to the air-water interface, and that will reduce the sorption of the other chemicals. And so I started working on that, and I'm getting some really interesting breakthrough curves. You get these snow plowing effects that, if you have chemicals at different with different KD, one can actually increase concentration above relative concentration 1, and so you can get something interesting. This was not released, we have not yet published that, but it's quite interesting. Nitrogen species. So this is something which we have in the code from 90s, that you can do these first order degradation chains. And when you apply it for, let's say, nitrogen species, you can start from urea, you can go to ammonium, nitrite, nitrate, nitrous oxide. Each of these chemicals can have completely different reactions, right? This can be tracer, this can be retarded chemicals, which can also be volatile. This can be tracers again, etc. There's a lot of applications of this. When we started working on that with Jan Hofmans, I did a large literature search to find what the constant in this system should be, what this nitrification constant should be, what the sorption should be, etc. And I believe we published that in one paper with Jan Hofmans. And we also apply that in multiple applications already. So this is an interesting applications where I work with Lyon on the flow and transport in the rice fields. So we analyze complete water balance, but then also complete nutrient balance with applications of ammonium, nitrate, volatilization to the atmosphere, uptake of nitrogen species by plants, nitrogen leaching, etc. Okay, that's it. So, questions?
All right, thanks so much for the extensive explanation about the modules, but also it was interesting to hear about Van Gnochten, for me at least.
Okay.
So, because time is limited, maybe I leave it for questions. So please raise your hand or for if you have any questions for Jirka. And there are many pluses coming for you with icons. Is there any questions from the audience? Maybe I can then start with my question, because for us, of course, this C-RIDE module is very interesting, and what you said for microplastics. So my assumption is that within this microplastic or colloid transport codes, it can be modified for perhaps different size bins of microplastics, which obviously have different properties than the colloid itself. And also, is it possible to adopt it for different shapes? And is it like, because I mainly work with atmospheric models, and there we can have different size bins of colloids or dust particles, and some bins for microplastics separately. So my question is generally about these different properties of microplastics, that whether that can be included in the model.
Yeah, well, so currently we just solved this equation, right?
Yeah.
And then we characterize particles basically by attachment coefficients. And so, yeah, if you have different sizes, you get different attachment coefficients or different straining coefficients. If you have different shapes, you get different straining, different attachment coefficients. But currently, we do not have it written in a way that you would have multiple pools of microplastics of different sizes and different shapes and their interactions. So that was on my list, like as a potential future development here, right?
Yeah, which hopefully can be used for SOILPROM, because we are also very much interested in it.
Yeah. So yeah, currently we don't have it like that, right?
Yeah, but it's possible. Yeah.
All the applications so far were always with the focus on one particular thing, like viruses, right? And then they are all the same size, or colloids of certain size, etc. So we don't have applications for mixtures of different sizes.
Yeah.
And that would need to be studied, right?
Yeah.
And I'm currently working with a group in China where we are looking at the colloids of different sizes and their simultaneous transport. And then obviously you get a question also how to analyze it, right? Because how to analyze colloids of different sizes in the breakthrough curves. And what they are doing is they are attaching DNA to different colloids of different sizes, and then we can distinguish between, in the breakthrough between these different colloids of different sizes.
Yeah.
And so we are just finishing actually paper on to submit it, so it's not yet done.
All right. Yes. Okay. Thanks, Jos. Do you want to continue?
Hi, Jos.
Okay. Hi,
It's
Jirka.
been a while.
Well, thanks for this very complete overview. It's very impressive, and also how you cooperate with a lot of people in different applications. It's nice that you are joining this SOILPROM project.
Yeah.
I will be mainly involved with the microplastics, so I think I fully agree with you that we should, I think, also look for some other concept that especially look at the size of the microplastics, which is considerably larger than the colloids. But you already mentioned that aspect. The other thing that triggered a bit my attention that you said about this preferential flow. That's an issue, micropores, macropores, that's quite important. You have those concepts on dual permeability, dual porosity, but you also made the remark that it is still a headache. And I think that is for many soil physicists. Have you any idea to make improvements with respect to those macropore leaching? Because we think that is a very important aspect for the contamination of groundwater. Any ideas about going further than this, well, dual permeability, which we know that it's not, in many cases, not physically right?
Yeah. It's quite difficult to implement something into process-based models, right? You can have some stochastic approaches and transfer functions and try to account for the preferential flow. So when I started in this field, there were these two different approaches how to address solute transport, right? One was pushed by Rien van Genuchten, which were these process-based models based on CD equations, Richards equation. And then the other approach was the stochastic approach by Bill Jury with his transfer functions, right?
Yeah.
And obviously these systems would give very different answers, but it is difficult to implement the stochastic system into our deterministic models, right?
Yeah.
Unless we do some, Monte Carlo simulations with many different parameters, many different realizations.
Yeah, we need something in between probably. And
if I had more time to talk about preferential flow, I would say it's the most frustrating process which we need to address, right? And it comes in waves that people are working on that a lot, like in the 90s, and then they abandon it. They basically give up. Then young people come with the new ideas. I'm not a young person, so I leave it to the young people to come with new ideas. Giuseppe,
now, perhaps we can explore it a bit in this project to see how we can address this, because I think it's quite important for microplastics.
Oh, yeah, certainly. It is, yeah.
Okay, Marus, I give it back to you, because I see we are a bit running out of time, so perhaps there are other people who want to...
I reviewed your paper recently on microplastics.
Okay, thank you.
Which you probably noticed, right? So.
Yeah.
Okay, so I'm checking there's no hands or question, but is there any question? Oh, yes, Gian, please.
Yeah, thanks for the very, very interesting presentation. It's very informative. And I just have a question about phosphorus. So you mentioned a lot about this HYDRUS can work for water and solute transport, and you also mentioned like nutrients. I'm just wondering for phosphorus, is it has it been used for simulating phosphorus losses? You did mention nitrogen. I noticed that, but I'm just wondering for phosphorus.
You see, I have never actually worked on phosphorus, right? So whenever somebody asks me like that, I just go to the HYDRUS website, right?
Yeah.
And I do the search, right? And you can see that there is one in 24, another one in 24, another one in yeah, just 5 papers just this year. And yeah, so there is quite a few applications. I know that phosphorus, it's more difficult because there the experimental evidence actually is that it moves faster than what you would predict with the retardation, right? And so maybe there is need to use this colloid facilitated transport for describing it. But people are certainly using HYDRUS for this as well, just using the simple KD approach. But I have never worked on phosphorus myself, so.
Yeah, okay. Yeah, thanks. Yeah, I will check those papers.
But yeah, I suggest always to visit HYDRUS website. We try to, to have there as much information as possible. And so it's easy to search this, right? And you can see that there is thousands of applications. So we list these applications, but we don't read them. You follow the Van Genuchten concept, you either read or write. You can't do both.
Okay, thanks a lot.
Thanks, Gian. There is another question from Remigio.
Yeah, from Ram. Actually, this is a follow-up. Thank you very much for a very great presentation. Actually, I learned a lot actually about HYDRUS, and probably to make things more complicated, and a follow-up to Gian's question actually, because I'm also working on phosphorus and sediments, and that's a big problem with macropore flow actually. So the conventional knowledge is that phosphorus flows with the surface runoff, but in reality, it's not. There's lots of evidence actually that it flows through the porous part of the soil, and I guess that's one of the challenges actually, that perhaps we can work together. Just the partitioning of these things, actually, phosphorus sediments that flows through the macropores, actually, is just a headache. So.
Yeah, well, we are now, as I mentioned before, right, we have this modfold package. So we are developing this coupling between HYDRUS and KINEROS, which is for overland flow. And KINEROS can do the overland flow, it can do sedimentation transport or transport of sediments or erosion at the surface. And it can do these solute transport as well. And so we are developing it right now, and again we are just writing a paper about it, how like different KDs have these different compounds, how they affect the transport in the overland flow, whether it's available for the transfer to the overland flow or not. And so we are developing this concept, but applications, that's gonna be on you guys.
Thanks.
You won't see me in the field.
All right.
What time do you guys have?
I
6,
think
right?
we are just in time.
Happy time.
So...
You miss happy hours today.
Yes, and I don't see any other question being raised. Then thanks so much, Jirka, for the nice presentation, for your time, and your colleague Giuseppe for being present, and everybody